Now we're going to apply what we've seen to this function that people selected out of the home, where g of x is 4 times the quantity 1 over x, excuse me, plus 1 over x squared. Okay. Now, over here, I've actually constructed the 1 over x and 1 over x squared graphs. Okay. 1 over x goes through the point 1, 1, 2, 1/2, and 1/2, 2. So this white curve can represent 1 over x in the first quadrant. 1 over x squared goes through the point 1, 1, just like 1 over x does, but it goes through the point 2, 1/4. So it's only half as high as the x squared graph when x equals 2, and through 1/2, 4. So it's twice as high as the y equals 1 over x graph when we get to x equals 1/2, so that the graph looks something like this orange graph. Okay, and then 1 over x squared is symmetric about the y-axis. If we replace x by negative x, we still get the same thing. So all these points reflect over here, and the graph is going to look like this. And the graph of the 1 over x squared is going to look like this. The graph of the 1 over x is symmetric with respect to the origin, so it's going to look like this. When we add the two graphs, okay, on this side it's not real interesting, on this side it is kind of interesting. First of all, we note that this graph, when x equals -1, we get +1 for this graph and -1 for this graph, so that the two values of 1 over x and 1 over x squared will add up to 0, so that our result would be 0. So that if we put a point here, a red point here, to represent the 1 over x plus 1 over x squared graph, I didn't include the 4 in this. I'm just graphing 1 over x plus 1 over x squared. So we see that just from the two graphs that the graphs are on equal and opposite distances from the x-axis, or equal and opposite displacements, so that the y values add up to 0, and this function will be 0 when x equals -1. Now, when x is between -1 and 0, this graph is higher than this graph is low, because remember, between 1 and 0, the orange graph is higher than the white graph. So the positive is going to be greater than the negative. So when we add the 1 over x, which would be the negative here, to the 1 over x squared, which would be positive, we're adding a negative number to a positive number, but the positive number has a greater magnitude than the negative number. Another way to see it just is we're here, we have to go up higher to get to this graph, and we got to go down to get to this graph. I just had my head in the way. But from here up to this graph is further than it is from here down to this graph, so the positive is bigger than the negative, and the result is that the sum of the two is positive, so that 1 over x plus 1 over x squared is positive between x equals -1 and x equals 0. To the left of -1, just the opposite is true. The 1 over x graph is further from the axis than the 1 over x squared graph. And you can see that over here, how the 1 over x squared graph goes in closer to the x-axis than the 1 over x graph. Okay, so that means that we're going to come down into the negatives, and we're going to stay there, because the 1 over x squared graph is always lower after we get past 1 than the y equals x graph. So on this side, the 1 over x graph is always further from the axis than the 1 over x squared graph, meaning that the negative is bigger than the positive, so the result is negative. However, both of these graphs fairly rapidly approach the x-axis, so that values get really tiny, so that when we add the two values, the tiny negative value we get from 1 over x to the even tinier positive value we get for 1 over x squared, we get a negative, but it's going to be pretty close to 0. So despite the fact that we come down below the axis, we got to return pretty quickly and approach the x-axis as an asymptote. Now, we should understand the numbers and the behavior of the graphs well enough to understand this way of picturing the graph before we ever apply the calculus. Okay, well, let's apply the calculus now. The derivative of the g of x function is easily calculated. I've calculated it. As is the second derivative. You can verify the derivative in the second derivative. Critical points occur when the derivative is equal to 0, so we set the expression for the derivative equal to 0. Now, the g prime of x would contain a factor of 4 times all this, but 4 is not going to be 0. It's this thing that's going to be 0. So g prime of x is going to be 0 when the quantity in the parentheses is 0. We get this. We multiply by negative x cubed. We get x plus 2 equals 0. A solution x equals negative 2. Meaning that our critical point, we only have one critical point. It occurs at x equals negative 2. Now, when I drew this, I put the low point, it looks like about negative 1.5. Okay, but I didn't have a real accurate graph, and I'm not making any excuses. I wasn't overly careful with the way I constructed the graph. Had I been a little more careful, the low point would have occurred over here. So we see that calculus gives us a correction to what we get when we use standard pre-calculus graphing techniques, and allows us to determine that the minimum of this thing, if I'm right about having a minimum over here somewhere, is probably going to occur at x equals negative 2. Now we're going to verify that. Okay, we've got our critical point. That's our only candidate for a maximum or a minimum. We take our second derivative and evaluate that when x equals negative 2. And we get, well, if we calculate it out, it's clear that we're going to get a positive. When we evaluate this term and this term, it's pretty clear that the negative we get on this term is smaller than the positive we get on this term, so that the second derivative is positive, which makes the graph concave up, which does give us a minimum at x equals negative 2. The real minimum, the relative minimum, therefore, occurs at x equals negative 2, and we can get the point at which that occurs. It's at negative 2, and then we evaluate g of x at negative 2. 1 over negative 2 plus 1 over negative 2 quantity squared, and do the arithmetic and complete the parentheses while we're at it. And we get negative 2, negative 1. So that, if I want to redraw this graph more accurately, I'll do it in such a way that the relative minimum occurs below negative 2 and actually at a value of negative 1. And I'm starting to question that value, negative 1. Oh yeah, okay. This includes the factor 4. Okay. This graph is not going to get down to negative 1. I mean, here's negative 1. Okay, and if you just think about it, you see that the graph can't possibly go that low. The graph of 4 times 1 over x plus 1 over x squared will have the minimum here. And I'm going to sketch that, and we'll come back and talk about it for just a short time. Okay, before, when I drew this graph, I had a pretty bad error. I came down to this point, and the graph kind of had an awkward curve there, and I was aware of the awkwardness. Thought about it, but I didn't think about it very deeply because we were in class, and then I started accepting what I'd done. If we're adding the values of the 1 over x, the white 1 over x function, and the orange 1 over x squared function, the values are both 1 here, so we would add the 1 for the one graph and the 1 for the other graph and get a value of 2. So the point on the red graph, the 1 over x plus 1 over x squared graph, should be at 1, 2. It should be twice as high as this point. And that's going to give us a much better looking curve. So now, when I do the final graph of y equals 4 times 1 over x plus 1 over x squared, it has the characteristics of this graph. It's just that this low point is over where it should be, below x equals negative 2. That's where our relative minimum occurs. and that relative minimum occurs at the point -2, -1, as we calculated using our calculus, and we wouldn't have been able to get that if we hadn't had the calculus. We could get this much without the calculus, and we could get a pretty good approximation of the graph if we made a very careful picture here, but we would not be able to verify that the minimum really is at -2, -1. The relative minimum. Okay, so here's a refinement of this graph and a correction that I should have made when I did this graph originally. The other thing about this problem is that this function is defined in the interval from -4 to 5, from x equals -4 to 5, and we're trying to find the maximum and the minimum on that interval. Okay, well, it's pretty clear from the asymptotic nature of this approach, this function's never going to go below y equals -1. And on this side of the axis, the function is always positive, so certainly we're not going to go down below y equals -1. So no matter how far we go over this way, and we only have to go over to -4, that'd be about here, this graph is clearly never going to be less than -1. So -1 is the minimum on the entire interval. The maximum, well, there is no maximum because we have vertical asymptotes on both sides of the positive x-axis. So the function can go as high as, the function exceeds all bounds. There's no limit to how high the function gets. So there is no maximum. So we conclude that, okay, there's no maximums. X goes to 0, g of x goes to infinity. We check the endpoints then. We have our relative minimum. There's no maximum. There's no relative maximum. We check the endpoints of the interval to see if one of them maybe is lower than our relative minimum. We see at -4, g of -4 is -3/8. That's not going to be lower than -1. And at 5, it's 24/25. And that's certainly not going to be less than our relative minimum. So neither of these is less than -1, so the minimum does occur when x equals -2, and there's no maximum on this interval.